Hi again, everyone. Today we're in section 5.1 of statistics and we're learning about probability rules. So I'm going to show you how to apply the rules of probabilities, how to compute and interpret probabilities using the empirical method, and how to compute and interpret probabilities using the classical method. So let's get started. Probability is a measure of the likelihood of a random phenomenon or chance behavior occurring. Probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. For example, if you flip a coin, there's no way to know whether the next flip will give you heads or tails, but you can know that about 50% of the time you'll get heads and about 50% of the time you'll get tails. So there's uncertainty in the short term because you don't know what the next result will be, but probability tells us what the long-term proportion of a certain outcome will be. That brings us to the law of large numbers, which says as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. While we're talking about the law of large numbers, I thought it would be helpful to see a demonstration of the law of large numbers. So what we're going to do is some simulated coin flips. This is an applet that comes embedded in MyLabs Plus. If you'd like to try this yourself, you can log into MyLabs Plus, click on Tools for Success, then click on Applets, and then click on Simulating the Probability of a Head. And what we have here is that they're going to simulate a coin flip for us, either one flip or 5 or 1,000, and they're going to show us here the total accumulated number of heads and the total number of coin flips and the proportion of heads that we've obtained. And then on the graph we have coin flips on the x-axis and proportion of heads on the y-axis, and right here is the 0.5 line, and what we expect is that in the long run the proportion of heads should approach 0.5. So the graph should eventually get very close to this line and then just ride along this line. Let's see what happens. So I'm going to flip the coin one time and we get tails. So right now we have 0 heads out of one flip for a proportion of 0, which you see here. And then flip again and we have a second tails. So right now we're at 0 heads out of 2 attempts, so 0%, and flip again, another tails, so still at 0%, flip again, another tails, and flip again. This time we got heads. So we have 1 head out of 5 flips for a proportion of 0.2, so our graph is here. And let's go a few more times. Okay, so you can see that now we are at a total of 4 heads out of 10 flips for a proportion of 0.4. So we're getting a little closer to that 0.5 line. Let's now have the computer flip the coin for us 5 times. We now have a total of 7 heads out of 15 total flips for a proportion of 0.4667 heads. So notice how we are approaching that 0.5 line. We did touch the 0.5 line once, but then we went away from it, and now it's going to come back toward it. Let's have the computer flip 5 more times. Okay, now we are at 9 heads out of 20 tries, so 0.45 or 45% of our attempts have been heads, and you can see that we're getting close to the 0.5 line, still staying pretty much below it, but this is the law of large numbers, and we really have not flipped the coin a large number of times yet. Let's have the computer flip 1,000 times for us. Okay, at 1,000 times you can see that the graph begins to hone in on this 0.5 line. Right now at 1,020 flips we have 0.5206 proportion of heads, and let's flip a few more 1,000 times. After 4,020 flips, I'm now at a proportion of 0.5065. So that's very close to 0.5. We could flip about 5,000 more times. And now we're at 9,020 flips, and the proportion of heads is 0.5007. So you see these wide swings that we saw at the beginning? The more flips we do, the closer we get to 0.5, and those wide swings disappear. So what the law of large numbers says is that in the long run, the proportion of times you observe an event will approach its true probability. Now we need to get some vocabulary so we can talk about how to work some of these problems together. In probability, an experiment is any process that can be repeated in which the results are uncertain. So, for example, flipping a coin would be an experiment, rolling a die would be an experiment, drawing a card out of a deck of cards would be an experiment. And the sample space, S, of a probability experiment is the collection of all the possible outcomes. So the sample space for flipping a coin is heads or tails. The sample space for rolling a die is 1, 2, 3, 4, 5, or 6. And an event is any collection of outcomes from a probability experiment. An event may consist of one outcome or more than one outcome. In general, events are denoted using capital letters such as capital E. So let's go through an example together. This says, suppose a probability experiment consists of rolling a single fair die. Determine the sample space. Well, remember the sample space is the collection of all possible outcomes. So if you're rolling a single fair die, the collection of all possible outcomes is 1, 2, 3, 4, 5, or 6. Then for part B, define the event E as roll an even number. Let's list all of the outcomes in event E. So we look at the sample space, and all of the outcomes in the sample space that fit this description are 2, 4, and 6. So event E consists of outcomes 2, 4, and 6. And then let's define event F as rolling a number greater than 3. So go back to the sample space and find the outcomes that fit the description of being greater than 3. And that would be 4, 5, and 6. So event F consists of outcomes 4, 5, and 6. Now the notation P parentheses E means the probability that event E occurs. So when we read this, we say probability of E. And here are the two rules of probabilities. 1, the probability of any event E, which we write as P parentheses E, must be greater than or equal to 0 and less than or equal to 1. In other words, probabilities always have to be between 0 and 1. And the second rule of probabilities is that the sum of the probabilities of all outcomes must equal 1. So probabilities always have to be between 0 and 1, and the sum of the probabilities of all outcomes must equal 1. Now, a probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy both of the rules of probabilities. So here we have a table from your textbook, and this says the color of a plain M&M milk chocolate candy can be brown, yellow, red, blue, orange, or green. Suppose a candy is randomly selected from a bag. The table shows each color and the probability of drawing that color. And so we want to verify that this is a probability model. So it has to do two things. It has to have each probability somewhere between 0 and 1, and the sum of all the probabilities has to equal 1. So let's just look at the table and verify that each of the probabilities is somewhere between 0 and 1. So check. And then 2, we have to make sure that the sum of all the probabilities adds up to 1, and it does. So this is a valid probability model. Now, if the probability of an event is 0, then that event is totally impossible. And if the probability of an event is 1, then that event is absolutely certain. And remember that it's not possible for a probability to be less than 0 or greater than 1. So all other probabilities must be somewhere between impossible and certain. So somewhere between 0 and 1. An event with a probability of 0.75 will occur about 75 times out of 100. This doesn't mean that it has to occur exactly 75 times out of 100, just that we can expect a long-term probability of about 75 out of 100. So just like we saw with the coin flips, to have a probability of heads at 0.5 doesn't mean that out of 1,000 flips exactly 500 will be heads. It only means that about 500 would be heads. Now, an unusual event is any event that has a low probability of occurring, and we have to put a number on that so that we're all thinking the same. Typically, an event with a probability of less than 0.05 is considered unusual, but this is not set in stone, and it does change depending on the event in view. For example, if I told you that the chance of rain tomorrow is 5%, you'd probably say, well, it's not going to rain, so that wouldn't make much difference to you. But if I told you that if you leave your house today, the probability of getting killed in a car accident is 5%, you'd probably stay home. So what's considered unusual kind of changes depending on what the stakes are, but typically in a textbook, anything with a probability of less than 0.05 is considered unusual. Now let's talk about approximating probabilities using the empirical approach. The probability of an event E is approximately the number of times event E is observed divided by the number of repetitions of the experiment. So the probability of E is approximately the relative frequency of E. That is the frequency divided by the number of trials. So we're very familiar with relative frequency from chapter 2, and I just want to let you know that this squiggly equal mark means approximately, and it typically means that a value has been rounded off. So here's an example. A pit boss wants to approximate the probability of rolling a 7 using a pair of dice that have been in use for a while. To do this, he rolls the dice 100 times and records 15 sevens. What is the empirical probability of this pair of dice rolling a 7? Okay, so empirical means observed, and this is just going to be the relative frequency of rolling a 7. So we're going to say the probability of rolling a 7 is 15 observations over 100 total trials, and so it's 3 out of 20. If you need to express it in fraction form, it's 3 out of 20, or if you want to go to decimal form, it's 0.15. Now do watch for instructions in MyLabs Plus that will tell you whether to submit your answer in fraction form or in decimal form. Okay, now we're going to build a probability model. This says the data in the table represent the results of a survey in which 200 people were asked their means of travel to work. Use the survey data to build a probability model for means of travel to work. So here we have our table, and these frequencies add up to 200. So to determine the probability for each mode of travel, what we'll do is take the frequency and divide by 200. Driving alone has a probability of 153 out of 200, so that's equal to 0.765. Carpooling is 22 out of 200, so 0.11. Public transportation is 10 out of 200, so 0.05. Walking is 5 out of 200, so 0.025. Other means has 3 out of 200, so that's going to be 0.015. And working at home is going to be 7 out of 200, so that's going to be 0.035. And so I hope you see that a probability model is really no different from a relative frequency distribution. Now let's take that probability model, and it says estimate the probability that a randomly selected individual carpools to work. Well, carpooling has a probability of 0.11, so I would say the probability that a randomly selected individual carpools is 0.11. In other words, out of 100 randomly selected people, we can expect that about 11 of them will be carpoolers. And then part C, would it be unusual to randomly select an individual who walks to work? Well, if we have a randomly selected group of people, our probability model is telling us that only about 2.5% of them walk to work. And certainly 2.5% is less than 5%, so I would say yes, it would be unusual to randomly select someone who walks to work. Now let's talk about the classical method of computing probability. The classical method of computing probabilities requires equally likely outcomes, and that is the key on classical method. An experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. So to compute probability using the classical method, we say that if an experiment has equally likely outcomes, then the probability of an event E is the number of ways that E can occur divided by the number of possible outcomes. And now let's look at example 5 together. It says a pair of fair dice is rolled. The sample space is shown below. So here we have every possible outcome for rolling a pair of dice. And it says compute the probability of rolling a 7. Well, we have 36 possible outcomes here. And then the outcomes for 7 are 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. And there are no other pairs of dice that add up to 7. So the probability of rolling a 7 is going to be 6 outcomes out of a total of 36 possibilities. So 1/6, if you need your answer in fraction form, or in decimal form, that is approximately 0.167. And now let's compute the probability of rolling snake eyes, or in other words, rolling a 2. So there's only one way to roll a 2, and that is that each die has a 1. So the probability of rolling a 2 is 1 out of 36, or approximately 0.028. And then it says comment on the likelihood of rolling a 7 versus rolling a 2. Well, you're 6 times more likely to roll a 7 than a 2 because there are 6 ways to roll a 7 and only 1 way to roll a 2. Now example 6. Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, and Marissa all want to go to the concert with her. To be fair, Sophia randomly selects the 2 people who can go with her. Determine the sample space of the experiment. In other words, we need to list all the possible simple random samples of size n equals 2. Well, she could pick Yolanda and Michael, or Yolanda and Kevin, or Yolanda and Marissa. Or she could have Michael and Kevin, Michael and Marissa, or Kevin and Marissa. And that's really all of the possibilities for selecting 2 people. Now it says compute the probability of the event Michael and Kevin attend the concert. Well, out of 6 different possibilities here, Michael and Kevin are one of those possibilities. So the probability that she chooses Michael and Kevin is 1 out of 6. 1 Michael and Kevin pair out of 6 possibilities. So that's fraction form, or if you need that in decimal form, it is approximately 0.167. And then it says compute the probability of the event Marissa attends the concert. Well, if we look back at our possibilities, Marissa's name comes up in 3 of the pairs. So the probability that Marissa attends the concert is going to be 3 out of a total of 6 possibilities. So in fraction form, that's 1/2, or in decimal form, that's 0.5. And then it says interpret the probability in part C. Well, we know that if Sophia repeated over and over the experiment of choosing 2 people, then about 50% of the time we would expect Marissa's name to be chosen. And the last type of probability we want to talk about is subjective probability, and we're not going to dwell on it very much, but it does exist, so I thought we'd talk about it just for a second. The subjective probability of an outcome is a probability obtained on the basis of personal judgment. That is a sheer guess. Sometimes this is the only way to assign a probability. It may be impossible to conduct an experiment or to use observed data. For example, if a reporter asks an economist what the probability is of a world recession, and the economist says he thinks it's about 5%, he's making a guess. There have not been any trials conducted. There's no frequency distribution for him to look at. There's no set of equally likely outcomes, so it's really just a guess. A situation like this would be too complex for anybody to do any real calculations. So this is an example of subjective probability. And since with subjective probability you're just talking about personal judgment, there's no right or wrong. So there's no way for us to evaluate you on that. So you won't see subjective probability problems in the homework. That would be crazy. But I did just want to bring it up so that when you see people in the news making predictions and saying there's a 50% chance of this or 25% chance of that, you'll know that they're not always using the probability methods we've studied. Sometimes they really are just using what's called subjective probability, so there's no calculation behind it.